Good morning, class. I'll just quickly share my screen with you so we can start the class. I can see we have a full class today. Okay, so we are still talking about the atomic structure. I'll quickly do a brief recap of what we learned on Wednesday. We concluded that atoms are composed of three main subatomic particles: the electron, proton, and neutron. And that most of the mass of the atom is concentrated in the nucleus of the atom. That the protons and neutrons are located within the nucleus, while the electrons exist outside of the nucleus. In stable atoms, the number of protons is equal to the number of electrons. The type of atom is determined by the number of protons it has, and the number of protons in an atom is equal to the atomic number, while the sum of the number of protons and neutrons in a particular atom is said to be... Yes, sir?
They are no longer seeing your screen.
Oh, really?
Because you decided to disable everybody because of the noise. So they are no longer seeing your screen.
Okay.
Yes. So you share your screen.
Again, okay.
Yes, ma'am.
And now, U.S. Secretary of State Antony Blinken says he made it clear to Prime Minister Benjamin Netanyahu.
I'm going to make you the host again so that you'll be able to do that.
Okay, all right.
Whether you can share your screen. Check whether you can share your screen.
Okay, let me see. Host disabled participant screen sharing. That's what it's still saying. And you're still the host from what I can see here. Okay. Okay. I believe I'm sharing my screen now. So I stopped at the sum of the number of protons and neutrons, referred to as the atomic mass. And you could also call it the mass number. And the valence electrons are the outermost electrons. And then we talked about Einstein's equation, which was rewritten to be lambda over h over mv. V being the velocity of an electron, replacing c, which represented the speed. And then we also looked at the uncertainty principle. And then we went on to quantum mechanics, where we talked about Erwin Schrödinger and the use of the mathematical equations of wave motion to generate a series of wave equations, which we use to describe the electron behavior in an atom. And I remember I did mention that the square of the wave equation gives a probability density map of where an electron has a certain statistical likelihood of being at any given instant time. And then we went on to the quantum numbers.
Share your screen again, ma.
Oh, okay.
And check, once you share your screen, check the security that they are able to chat and rename themselves only. All other things.
Okay.
Yes. Thank you.
Host disabled participant screen sharing, sir.
Yes, I will do that. I will get myself, because they are no longer seeing your
My screen, yes.
I wanted the recording to be done. That was why. So it's being recorded now. So go ahead, man.
the president of the US.
Yes, ma.
They on the sidelines of opening in Dubai.
Can you see my screen, sir?
Yes, they can see your screen.
Okay, all right. So I think I'm in order now.
Yes, ma.
All right, sir. Thank you, sir. Okay, so I said an orbital is described by a set of 3 quantum numbers. And that you can actually look at these quantum numbers like coordinates. Usually when we draw a graph, we have 3 coordinates, coordinate X, Y, and Z. And so we looked at this table where we had the where we have the quantum numbers of the electrons in atoms. And we looked at their names, being the principal quantum number, angular momentum quantum number, magnetic quantum number, and the spin quantum number. We also have the symbols. Principal quantum number being L, angular momentum quantum number being L, magnetic quantum number and M subscript L, and then the spin quantum number M subscript S. Please, I would like to excuse myself for just 2 minutes. Okay, so going back to our class, sorry for the distraction. I'd forgotten that this class is actually clashing with a lab that I have right now. And their lab notes are with me. So we also looked at their permitted values for the principal quantum number, positive integers like 1, 2, 3, 4, 5, 6, and so on. And then the angular momentum, 0 to n minus 1. While for the magnetic quantum number, integers from minus L to 0 up to plus L. And then the spin quantum number being plus half or minus half. We also looked at the properties for the principal quantum number. Therefore, the energy tells us the energy level. The angular momentum talks about the orbital shape, while the magnetic quantum number talks about orbital orientation, and then the spin quantum number, from the name, it tells us about the direction of the electron spin. The angular momentum quantum number can as well be referred to as the azimuthal quantum number. So going on to the principal quantum number, we said the principal quantum number describes the energy level on which the orbital resides. And the value of our n is usually greater than 0. Just and then for the azimuthal quantum number, we have, it tells us about the electron's angular momentum. Now, the values that are allowed are from 0 to n minus 1. So, for example, if our n is 1, our L will be 0, because that will be 1 minus 1. If our n is 2, our L will equal 0 or 1. We have a table here showing us the angular momentum for each value of L. For 0, it tells us that there is no angular momentum. For L equals 1, tells us that the angular momentum is linear. For 2, it tells us that it is 2-directional. And for 3, it is 3-directional. So the values of L relate to the most probable electron distribution. And the letter designations are used to designate the different values of L, which also gives us an information about the shapes of the orbital. For L equals 0, the orbital subshell is designated S. and we can see the orbital shape. Is referred to as sharp. For L equals 1, the subshell is P, which is principal. For L equals 2, the subshell is D, diffuse. For L equals 3, orbital subshell is F, which is fine. Now, for the magnetic quantum number, which is designated M, small m, subscript L. It talks about the orientation of an orbital with respect to a magnetic field. And it translates as the three-dimensional orientation of the orbital. So we could have values ranging from -L to +L. So if we have our L value being 0, our magnetic quantum number will be 0. Our orbital designation will be S. And the number of orbitals will be 1. Sorry. For L equals 1, we have our ML value. That's our magnetic quantum number value being -1, 0 to +1. And then our orbital designation being P, and the number of orbitals we have there are 3. For L equals 2, we have our ML values being -2, -1, 0, +1, as well as +2. The orbital designation is D, and the number of orbitals are 5. For L equals 3, we have our magnetic quantum number being -3, -2, -1, 0, +1, +2, +3, and our orbital designation being F, and the number of orbitals are 7. So that's where we got the SPDF from, the SPDF. Okay. So this table also gives us a broader view of these quantum numbers and their subshells. For n equals 1, 2, 3, 4, we can see the possible values of L. So this is a bit more comprehensive in terms of, in terms of the possible values of L and the subshell designation. So when we have our N equals 1, our possible value of L is 0, as we had earlier mentioned. Our subshell designation is 1s. And then the possible values of our ML is 0. The number of orbitals in the subshell is 1, while the total number of orbitals in the shell is 1. When our N equals 2, the possible values of L will be 0 and 1. And when it is 0, we know that the subshell is S. But because N is now 2, then our subshell will be 2S. And then when L is 1, it will be 2P. Then we have the possible values of our ML. For L equals 0, we have our possible value of ML to be 0. And then for L equals 1, still under N equals 2, we have our possible value of ML being 1, 0, and -1. We have a number of orbitals in the subshell being 1 and 3. And then the total number of orbitals in the shell will be 4. 1 plus 3 will give you 4. When you get to the next level, N equals 3. The possible values of L will be 0, 1, and 2. And each of them have their subshell designation, being 3S, 3P, and 3D, with a possible value of ML. For 3S, we have 0. For 3P, 1, 0, -1. For 3D, we have 2, 1, 0, -1, -2. Then the number of orbitals in the subshell is 1 for the 3S. For the 3P, we have 3. For the 3D, we have 5. So in total, 5 plus 3 plus 1 gives us a total number of orbitals in the shell being 9. For N equals 4, we have the possible values of L being 0, 1, 2, 3. We have our subshell designation being 4S, 4P, 4D, 4F. Our possible values of ML being 0 for 4S. For 4P, we have 1, 0, -1. For 4D, we have 2, 1, 0, -1, -2. Then for the 4F, we have 3, 2, 1, 0, -1, -2, -3. And the number of orbitals in subshell gives us a total of 1 plus 3 plus 5 plus 7, which is 16. So we also have this scientist who lived between these years, Otton Stern, 1888 to 1969, and then Walter Gerlach, 1889 to 1979. And they carried out an experiment. Stern carried out an experiment in 1922. And we have the pictorial diagram of what the experiment looked like. There was a furnace. We had silver atoms. We had our inhomogeneous magnetic field. And we had the classical prediction. So this led to the fourth quantum number that tells us the spin that the electrons could have at any given time. And there are only two values allowed. They're either plus half or minus half. From the diagram, it is spinning in the clockwise or the anti-clockwise direction. I have a scientist by the name Wolfgang Pauli, lived between 1900 to 1958. He didn't live for too long. But in 1925, he came up with a principle which we call the Pauli's exclusion principle. And he says that there can never be two or more equivalent electrons in an atom, for which in strong fields, the values of all quantum numbers, either n, your K1, K2, or your m, are the same. So that tells us that even when we have our angular momentum, the n value is the same, the L value being the same, and the ML value being the same, the spin will be different. So there will be something that will differentiate that electron from another electron. That's why he said there can never be two or more equivalent electrons. One or either of those values will differentiate that electron from another electron, even though they are electrons of the same atom. We also have another scientist by the name Frederick Hund, who lived between 1896 to 1997. He came up with the Hund's rule that talks about degenerate orbitals. And he said for degenerate orbitals, the lowest energy is attained when the electrons occupy separate orbitals with their spins unpaired. From the diagram, we can see 2s and 2p orbitals there. And from what he said the lowest energy is attained when the electrons occupy separate orbitals with their spins unpaired. So if you look at 2p, there are 3 electrons to be filled in. So you first go 1 in each of those boxes. And then you return back to pairing. You don't just, merge those electrons together. You have to first fill up each of those boxes before you can begin to pair. So my question is, what are degenerate orbitals? And it's very simple to explain. They are electron orbitals that have the same energy levels. And that's why you see that we're not picking electrons from the 2s. We're only considering, when I was explaining, I was only explaining those that are from the 2p, because they all have similar energy levels. In our basic chemistry, we are aware that our elements are represented by symbols. Like we have helium being H, capital H, small e. And would usually have 2 numbers by the symbols that tells us a bit more about the element. We have the atomic number as well as the mass number. In some instances, you could find the atomic number on the lower part and then the mass number on the higher part, as the subscript. Or you could find the atomic number on the superscript and then find the mass number on the subscript. But it's very easy to differentiate and know which is actually the mass number compared to the atomic number. You would not find the atomic numbers always come in whole figures. So you always find them in whole numbers. But it's possible for you to have mass numbers that are not in whole figures. So, trying to conclude our class, protons, we say, have a positive charge. Electrons have a negative charge. And in a neutral atom, the number of protons equals the number of electrons. And so the overall charge will be 0. An example we have here is helium. Helium is with an atomic number of 2. And that tells us that it has 2 protons. When it is stable, we said the number of protons equals the number of electrons. So as a neutral helium atom, the number of electrons will equal 2. Sometimes atoms will either gain or lose electrons. And when they do so, we refer to them as ions. These atoms can either gain electron to become negatively charged or lose electrons to become positively charged. When the ions are positively charged, we refer to them as cations. But when they are negatively charged, we refer to them as anions. So I'd like us to do a little practice. A little practice here. And for those who want to answer this question, you can just show by the raise of your hands. We have aluminium. We've been given the number of protons and the neutrons. Okay, I have Bimbola. Let me see. Hold on. Okay, so Bimbola Engman.
Yes, ma'am.
I shouldn't have called you because you don't even have your matric number here. Next time, please put your matric number there.
Okay, ma'am.
So are you ready to answer the question?
Yes, ma'am.
Okay, so what would the number of electrons be?
The number of the electron of the electron.
The atomic number
The atomic number is 13.
and then the atomic mass.
It's 27.
All right, thank you. So we have another one here. Let me see. We have fila. Okay, fila.
The proton the proton number is 47. The electron number
Okay.
is 47. The neutron number is 61. The atomic number is 47. The atomic mass is 108.
All right, thank you. Then I have uranium. Ecopore. Let me see. Is it echo or echo or echo? How do
Echo.
they pronounce your name?
Echo.
Eh?
Echo, ma.
Echo.
Echo. Echo.
Echo. Echo. Okay. All right. What's the number of protons?
Ma?
You wanted to answer the question.
Yes, ma.
Okay. Go on.
92, ma.
Okay. Electrons,
92.
neutrons,
146.
okay. Atomic number,
92.
atomic mass,
Atomic 238.03.
all right, thank you. Omokaru. Okay. Omokaru.
20.09. Yes, ma'am.
Yes, what's the charge?
+1.
The protons,
Proton is 19.
electrons.
Electron is also 19. Electron is 18.
Electrons.
18.
Uh,
I don't know. I think 19 plus 1.
okay.
20. The neutron is 20.098.
Okay. Then the atomic number.
Atomic number is 19.
Atomic mass.
39.09.
Okay, thank you. Okay. So we've come to the end of our class today. I will be sending the slides to you for your own read up. And I also want to suggest, because someone asked me in the last class if they should cram the years, the scientists carried out those experiments. I think you should, because the questions can actually come from any part of the course. So please do so. It's not too much for you to put in your head. I also want to encourage you not to just totally depend on the slides alone, but get a chemistry textbook. Any general chemistry textbook will be of use to you because it will cover all the basics of chemistry, both the organic, physical, inorganic, as well as the analytical part. So any textbook you find written as general chemistry should be good enough for you. And if after the whole thing you still have issues with some of the things we have talked about, you can always come to my office at the chemistry department. My office is just 2 doors away from the staff canteen. So if you're able to find your way to the staff canteen, it's very easy to locate my office. It's just 2 doors away from the staff canteen. And you will see on the door written Dr. A.O. Nature. I have someone raising their hands here. Dorcas Adedo. Trying to unmute you. Okay. Dorcas.
Sorry, Ma. I wanted to answer the question before, but someone already answered the question.
Okay, no problem. Finest. You don't have your matric number there. Ianu. Okay, let me unmute you. Ianu. Ianu.
I wanted to ask which textbook, O level or A level, would you recommend?
O level
Hello?
or A level?
Yes, ma'am.
It's A
Like,
levels, not secondary school textbooks. So
not okay, not secondary school textbooks.
no.
All right, ma'am. We can get one at the bookshop now.
Yes, you can.
Okay. Okay, ma'am.
Okay, so I think we've come to the end of the class. Next week, Dr. Dwekeze will be taking you for the week. Goodbye and have a pleasant semester. Bye.